Hi everyone, I am Wilmer, a PhD student at University of Valencia, Spain. I am going to present the work developed together with Juan and Miguel, professors and members of the Computer Science Department. The work is entitled Multi-Resolution Quality-Based Video Coding System for Dash Scenarios.
Nowadays, a great part of internet traffic is governed by multimedia content. Cisco report that is the more than 85%. This is largely to the conception of the content of platforms such as Netflix, Facebook, YouTube, TikTok, HBO, among others. Most of them provide the loading and conception of the video content can be online or on demand. A clear example for this behavior happening during the confinement generated by the COVID pandemic, where the 26% of global traffic was generated by the streaming platforms such as Netflix and YouTube, according to a report conducted by Zenby.
Currently, for video streaming, de facto technology adopted by the large part of industry is HTTP adapting streaming. There are several format specifications. However, the most widely used are HTTP live streaming and dynamic adaptive streaming over HTTP Dash. In Dash, videos are split into segments typical between 2 to 10 seconds, and each segment is encoded in different representations or combination of bitrate, resolution, FPS, codecs, etc. The representation of a video are specified using the media representation description file. This file contains all the metadata needed by the clients to enable a continuous adaptive video transmission depending on the changing network conditions. In order to provide the highest quality of experience, streaming system required efficient video encoding. Videos must obtain the highest quality with the lowest bitrate in the encoding phase to reduce the possible cause of QA degradation. Currently, most solutions perform variable bitrate encoding, where the encoder selects the appropriate bitrate based on complexity of each segment. With this premise, the following objective was set for this work. Encode each segment using different parameters to achieve a target quality using BMF. To have a direct impact in coding time and video size, and the resulting video should be compatible with enabled Dash players. Now, I will present our proposal. In this figure, we show the main components of the proposal. First, we have a data preparation component that performs dimensionality reduction and splits the resulting video. Next, we have the quality-based segment analysis component that finds the encoding parameters per segment to achieve the target quality. Finally, the adaptive segment encoders encodes each segment and different resolution using the parameters obtained by the previous module. As observed in the previous diagram, the system receives three inputs: a high resolution and a high quality video or a raw video, a list of resolution to generate the different representation for Dash, and the target quality to be achieved by each segment. A quality metric allows us to measure the subjective or objective quality of encoded or transcoded video. In this paper, we have selected the BMF quality metric. Its values can range from 0 to 100. Values close to 100 are considered high quality. The input video is processed by the dimensionality module. Here, a downscaling process is applied to the video, reducing its original resolution to a smaller one, with the objective of reducing the computational complexity in this analysis phase. For this process, the FFmpeg tool was used with the command shown in the slide. The resulting video will have a height of 240 pixels. As for the width, it is automatically calculated for the maintain the original aspect ratio. After this step, the scaled video goes into the segmentation module. This module splits the video segments of uniform size. The purpose of the segment analysis module is to determine the coding parameters that most closely approximate the quality obtained in the segment to the target quality predefined by the user. The module takes as an input target quality value, in this case a BMF value, and the aforementioned segments. Consequently, in an interactive process, each segment is analyzed to adjust the CRF value that most closely matches to the target quality value Qt. This procedure is equivalent to solving the convexes problem, where the function Q, which depends on the CRF value, what is known. Therefore, this optimization problem has been solved using the gradient descent strategy with adaptive step. We analyze this in the following. Before, I would like to mention that the constant rate factor, or CRF, is a constant quality encoding mode. This parameter is present in codecs HAUT, ABC, HEVC, AB1 or BP9, where the high CRF values mean a degradation of the video quality and therefore a low bitrate. The figure shows the algorithm to analyze each segment. The function receives as an input parameters the segment, the target quality, and initial value of CRF. The video is encoding and the calculated quality in a higher than the target quality, then the CRF value should be increased, otherwise it should be decreased. This process should be run interactability until convergence. The initial step is maintained until its sinks must be changed. In that case, the step absolute value is decreased by a factor of 2/3. Once the CRF value has been determined in distorted and returned, size it will be used as the unit value for the analysis of the next segment. We are making the hypothesis that the adjacent segments are likely to have similar complexity. The output of the segment analysis module is sequence of the serial values, once for each segment. These serial values will be used to encode the input video segments in a different resolution specified by the user. Next, I will show you the experiments performed to validate and evaluate the proposed system. The following section presents the testbed used in the experiment phase, the analysis of the base case to compare the proposal, and finally results comparing fixing versus proposed adaptive system are presented. 3 open source videos has been considered: Big Bang Bunny, Sintel, and Teaser Still. The videos are at 4K resolutions, 24 frames per second, and G4M RAW format. In order to approximate the proposal to a real scenario, the duration of the used videos is more than 10 minutes. The figure on the right shows the spatial temporal information of each frame of the videos, presented as the heat map to amplify the complexity of each sequence. The hardware used is described in the table 2. The entire proposed coding scheme is encapsulated in 2 Docker containers. The first container encapsulates the encoding system with the various components for the content preparation across the multiple representations. The second container encapsulates the quality analysis and provides support to different metrics. This container can take as an input the distorted video and the reference video for the analysis of the metrics with the full reference, reducing reference and no reference. The 2 containers shared a local volume to minimize the read-write operation on this or network traffic. On the other hand, the codec used for the encoding process is X264. As mentioned before, we have BMF as a reference quality metric. And as for the segment size, it was set to 4 seconds to obtain a compromise between encoding efficiency and flexibility to adapt the changed bandwidth flows. In this section, we show the consideration used to compare the fixed series of encoding of all segments of the video versus the proposed approach. Each round source video was encoding a different series of values in the range of 25 to 31 and at a 1080 resolution. A quality analysis of each output was performed where quality metrics such as BMF, ACM, and PSNR are considered. In addition, the encoding time and the size of the resulting file were recorded. The choices of series for the rest of the experiments that we fixed encoding was 67 because it's giving similar quality results to those obtained with the proposed approach. The results for all series can be found in this paper. This section analyzes the performance of the proposed interactive series of estimation algorithm. The first value analyzed at this point is the average time used by the algorithm to determine the series value for each segment. In this observed that its value varies depending on the nature of each video. For example, the average value used for BBE is 1.01 seconds per segment, 1.33 for CTL, and the highest value of 1.61 for TOS. On average, it can be said that this algorithm needs 34% of the time of the segments to find the encoded parameters of series, unlike other proposals that required 10% more. The number of interactions performed by the interactive algorithm until convergence is obtained, as it can be observed as the previous result with video with less interactions is BBB with 2.6 on average. However, for STL is research 2.94 interaction on average. The distribution of the different series values per segment and video can be seen in this figure. The series values used in BBB are in the range of 24 to 34. The most frequently repeat values are 27, 28, and 30. In the case of STL, it can be observed that the range is between 20 and 43, with the most frequently repeated value being 28, 27, and 26. As for TOS, the most frequent repeat values are 27 and 26, with a route very similar to TOS. In this section, we analyze the difference between the proposal approach and the base case described above. Figures 7, 8, and 9 show the difference in size per segment between the proposal and fixed encoding. Here, negative values represent a decrease in the size of the video when using the adaptive encoding, due to the adaptation provided by the algorithm. We have plotted the spatial information, the temporal information, and the size difference for each segment for STL encoding at 4K resolution. We can observe for this scenario that we have more gains in size when the temporal information is high. We see a positive correlation between these two variables, but we need to perform more experiments to validate this behavior. The following figure shows a comparison of the average bitrate obtained for two coding schemes, fixed and adaptive, and three videos, BBB, STL, and TOS, when the videos are coding at different resolutions. In a reddish tone, we show the results for BBB video. In a greenish tone, we show the results for STL video. In a bluish bluish tone we show the results for those videos. Darker tones correspond to the fixing approach while cleared ones correspond to the adaptive approach. As can be seen, the proposed adaptive scheme has a lower bitrate for all resolution and all videos. In the final experiment, we encode the 3 videos at the 5 resolution, using the fixed and adapting approaches. We obtained the quality achieved, size, and time to encode. For the proposal approach, the encoding time for 240 resolution includes the time needed to analyze each segment to obtain the CRFs. This analysis is performed only once as the obtained CRFs are used for all resolutions. Although only VMAP values are shown in the presentation, SSAM and p-scenario quality values were also calculated and are shown in the paper. This table shows the results for BBB video. On average, an improvement in size of 8.4% has been achieved. In terms of encoding time, an improvement of 2.5 minutes less when encoding all resolution. The data obtained for STL, they show that one average and an improvement in the resulting size of 12% has been achieved above the resolution. As for the encoding time, it increased by the 9 minutes with respect of the fixed CRF encoding for a resolution. For the toes, the average improvement when coding all resolution with respect to the total size is 12%. In terms of encoding time, the improvement is 7 minutes. As for the EVM values obtained, they are greater or equal to 90, which has been the selected target. In conclusion, an adaptive quality-based encoding scheme for Dash has been proposed in this work. Each video segment of a raw 4K input video is encoded to provide a target quality. An optimization problem is solved using gradient descent with adaptive step for each segment to obtain the CRF that achieves the target quality. This analysis is performing at low resolution to increase performance. The proposed algorithm performs in means of 3 interactions to converge. The proposal schemes has been compared with the use of the fixed CRF value per segment when applied to 3 videos and processing 5 resolution per video. Result shows that the proposed adaptive encoding achieves the target quality with a reduction between 8% and 12% of encoded video size. As the future work, we will compare the uniform split with a scene-based split and will encode each segment with different video codes like BP9, HABC, AV1, and BBC in a cloud environment to increase performance. Thank you for your attention.